Hi, and welcome to this introduction of the various techniques and methods that can be used to simulate seismic cycles. This presentation was put together by the current members of the Seismic Cycle Working Group of CIG. So I would like to thank my collaborators, Allison, Alice Gabriel, Lorraine Hwang, Dave May, Pierre Romanet, Paul Segall, and Luca Dal Zilio for their contributions. So we're going to start by a few motivations of why we want to simulate seismic cycles and how that can be useful. So typically, seismic cycle simulations can be used to explain observations, either seismological, geodetic, or geological, through a unified physical model of the lithosphere. So these simulations allow us to test ideas and concepts and to see how they could potentially explain observations. So an example of this is a simulation of earthquakes on the Park Field segment of the San Andreas Fault that explain, among other things, why the hypocenter of these earthquakes would change location from one event to the next within a sequence. Other applications of seismic cycle simulations is to understand processes that are not available with sufficient resolution observationally. So an example is to better understand the emergence of foreshocks preceding large earthquakes. So it's an example that was provided by Camila Catania and Paul Segall that described the clustering of foreshocks within the nucleation of a wider event that in this case was attributed to small-scale variations of normal stress that allowed the nucleation of smaller events. And of course, this spatial variability of normal stress is not an observation that is available at great depth in natural conditions. Another use is to make predictions based on theory about the type of ruptures and sequences that can be observed. So this example was provided by Deepa Melevidou and collaborators, where the theory of frictional sliding predicted a complex transition between slow and fast earthquakes that involves a bifurcation, showing a succession of slow and fast earthquakes. And so the theory was predicted this phenomenon, and that was later confirmed by laboratory experiments that explored that transition by varying the normal stress in a laboratory setting. Another application of these methods is to predict the recurrence pattern of earthquakes and better understand their predictability. This is an example produced by Xing Ni and myself that explored how the recurrence patterns of earthquakes changes with the frictional properties of the fault and the characteristics of the surrounding compliance zone. And as the characteristic weakening distance of earthquakes shrinks, there is a transition from quasi-periodic earthquakes to more chaotic sequences. And so if earthquakes faults are more and more unstable, it leads to a transition to sequences that are chaotic and deviate substantially from time and sleep predictable models. So to introduce these methods, we want to introduce first the different physical phenomena that take place in seismic cycles, and we're going to describe how they can be mathematically formulated with governing equations. So the basis of being able to model the evolution of stress on a fault is to have solid rocks that are described by elasticity. So we consider a continuum where formed by succession of representative volume elements, and conservation of linear momentum provides the elastodynamic equation, so the wave equation in 3D that describes the balance between stress, forces, and radiation of seismic waves. The conservation of angular momentum provides the symmetry of the stress tensor. And Hooke's law connects strain, so gradients of displacement, with the stress tensor. So this body, this elastic body, follows this governing equation, but is also subject to boundary conditions that can prescribe stress or displacements. Additionally, to model earthquakes, we consider the presence of internal fractures within the body on which displacement can occur. Another useful approximation of elasticity is the so-called quasi-dynamic approximation. In this simplification of the physics, we consider the elastostatic equilibrium, and so we ignore the radiation of seismic waves. This is a perfectly justifiable assumption if we're looking at timescales that are greater than the time it takes waves to leave the domain of interest. However, this approximation is not amenable to explaining fundamentally wave-driven phenomena such as supershear ruptures or other such ruptures that are fundamentally governed by how the waves radiate. So solving the wave equation is a hyperbolic problem. So it engages different numerical methods. And solving the elastostatic equilibrium is solving an elliptic equation that requires yet another baggage of tricks. For example, it can be solved with Fourier transforms or Green's functions if the domain is sufficiently simple. To incorporate seismic cycles within an elastic body, we need to consider the evolution of friction on a fault. So fault friction refers simply to the forces that resist the sliding between two solids, even if they can be separated by a gouge. To capture the constitutive behavior of fault friction, we can consider a spring slider assembly, where the loading on the fault is represented by this spring, and the frictional resistance is captured by this slider. So to model how the system evolves, we need a constitutive law that predicts the sliding velocity as a function of the stress, the temperature, and other state variables of the system. So what's fundamentally interesting about friction is that friction holds a memory of previous deformation, and that can be captured by a state variable. Here in this formulation, it is described as the size of microasperities. And so the evolution of the asperity size must be described by an evolution law that is independent from the friction law. To simulate two-dimensional or three-dimensional deformation, as opposed to simply a spring slider model, we need to augment this formulation to a three-dimensional formulation. So instead of a sliding velocity, we consider a velocity vector. And the typical assumption is that the sliding velocity is proportional to the traction applied on the fault surface. To simulate earthquakes, we need to consider more things than simple friction. For example, flash weakening or thermal pressurization that involves yet more physical processes. Additionally, several different types of frictional laws are currently being used and tested to represent frictional sliding. This formation in the lithosphere involves brittle failure, represented by friction, but also distributed deformation that can be described as viscoelastic or viscoelastoplastic, which is time-dependent. So viscoelasticity refers to the time-dependent accumulation of plastic strain in the country rocks, so away from the fault, by processes such as diffusion creep, dislocation creep, and other microphysical mechanisms. This can be represented in the simplest way by a spring dashpot assembly, where the stress is the spring, and the time-dependent deformation is captured by the dashpot. So the constitutive law for viscoelasticity is a scalar relationship between the strain rate, gamma, proportional to the stress or stress to a power. Again, if we want to simulate three-dimensional deformation, we need to find an equivalent formulation that involves strain tensor, stress tensor, as opposed to scalar quantities. So in a three-dimensional formulation, the plastic strain rate is proportional to the deviatoric stress tensor. So to find the governing equation of viscoelasticity, it is useful to separate the total strain tensor into its elastic and unelastic components. So we care about the total deformation, so the total strain, and the governing equation for the total strain resembles the one of elasticity, except that it has additional body forces that are a function of the plastic strain rate. The plastic strain rate itself is prescribed by constitutive laws that depend on stress, temperature, state variables, and can take the simple form of simply the deviatoric stress divided by a viscosity for diffusion creep, or a more complex expression involving a power law of stress and a temperature activation in the case of dislocation creep, for example. Other viscoelastic phenomena of importance, such as transient creep, can be modeled by incorporating a state variable into these formulations. The migration of fluids within the crust surrounding the faults can be described by linear poroelasticity, whereby a representative volume element is thought as a combination of solid matrix called the skeleton and fluid saturated connected pore space. And considering the fluid and the solid phases, the response is different in undrained and drained conditions, which represent the instantaneous response and the steady state response of the system. So this can be described by considering the conservation of momentum. So this provides this equilibrium between strain rate and radiation of seismic waves. But in a poroelastic medium, this introduces another body force, which is proportional to the gradient of the fluid content. Fluid then can migrate following a Darcy flow law. So the fluid flow is proportional to the gradient of pore pressure. But pore pressure is itself a function of the gradient of fluid content and the volumetric strain of the solid matrix. So here you have full coupling between the migration of fluid and the compressibility of the solid matrix. So with this introduction, we're going to go through various techniques that have been introduced successfully to simulate seismic cycles, and we have broken them down into three different categories based on the type of discretization that is being used. The first category manages to only discretize numerically the faults that are engaged in seismic cycles, and they are referred to as the boundary integral method. And different flavors of the boundary integral method come about whether we include or neglect the radiation of seismic waves, if we make further simplifications that allow more efficient methods, such as Fourier transforms. So we have a spectral boundary integral method that is very efficient. And if we ignore the radiation of seismic waves or not, whether we use the spectral method or not, it provides different declinations of this technique. The other category is involving discretization of the volume. So this also has different flavors, whether this the resulting method uses finite difference, finite element, or spectral elements. And the third category, well, is hybrid methods that combine these different techniques based on their various advantages. So we're going to describe different examples of applications of these methods. So the first one that we want to describe here is the fully dynamic boundary integral method. So for dislocations that are embedded in elastic material, the displacement anywhere in the solid is a linear function of fault slip. And so we can simply relate the displacement field to the history of fault slip through what we called Green's functions. So a triple integral of slip under fault through the history of time of deformation provides the displacement field at any point in space. So the advantage is that these Green's functions are often available in closed form. And so it allows to completely take into account the effect of the volume through these functions and focus simply on discretizing the history of sliding on the fault plane. And that reduces the dimension of the model space, and it is in a way more efficient. So an example of this is the Green's functions that relate slip under fault with stress under fault for mode 3 two-dimensional deformation. And you can see that there is a closed form solution between the slip S and the stress tau anywhere on the fault. So these are related through integrals. These integrals can be discretized numerically using the trapezoidal rule, leading to a solution that can be obtained by a series of matrix vector multiplications. So the method is computationally intensive, but it is quite versatile, right? So an example of this was provided by Baoning Wu, and it is the calculation of seismic cycles on faults that are separated by a step over. And the radiation of seismic waves from one fault segment that is currently rupturing modulates the shear and normal stresses on the subsequent fault that delays and sometimes accelerates rupture on the next segment. However, using the same technique on a three-dimensional model with a finite fault is currently computationally prohibitive without further modifications. So one such improvement of the fully dynamic boundary integral method is to take advantage of the convolution theorem of the Fourier transform and the computational efficiency of the fast Fourier transform to accelerate these computations. In fact, we can find closed form solutions that relate the history of slip under fault to the stress under fault that can be described in the Fourier domain. So an example of this here is showed for mode 2 for the fully dynamic stress interaction. And you can see that the static term in the Fourier domain is simply a transfer function between slip and stress. So it's a very trivial calculation. And the dynamic term is simply an integral of the history of deformation, but also involving a transfer function between slip rate and stress. So again, often these kernels of stress are available in closed form. And so we can do this calculation in the Fourier domain, which reduces the computational cost from n cubed to n squared log n. So dramatically improving the efficiency of the calculation. So this is an example of the spectral boundary integral method provided by Pierre Romanet that illustrates the SKEC sequence of earthquakes and aseismic slip, benchmark number BP7, that involves cycles of elastodynamic ruptures on a circular asperity embedded in rectangular plane of fault. Currently, the spectral boundary integral method is the most efficient method to simulate seismic cycles at the cost of the various simplifications that are involved, namely faults have to be planar. So to accelerate this calculation even more, we can in fact neglect the radiation of seismic wave in an approximation that is often referred to as radiation damping. So the static term remains the same, but the so-called dynamic term simplifies to this radiation damping term that is simply a function of the current instantaneous sliding velocity. So because we're losing an integral over the entire history of deformation, this reduces the computational cost quite a lot. So there's many examples of this method. This one was provided by myself that shows application of these methods for two-dimensional problems for which it is quite efficient. That documents the change in rupture styles and recurrence patterns as a function of physical properties of the system. However, using this method, the space domain, quasi-dynamic boundary integral method for three-dimensional problems with finite faults is still computationally extensive, and that limits the space of parameters that can be considered. So one way to accelerate the calculation is to use numerical tricks. One of them is using hierarchical matrices, so-called H-matrix method. And since the boundary integral method involves a lot of matrix vector multiplications, we can accelerate such simple operations by conducting blockwise singular value decomposition of these matrices and neglecting the high order terms. So this dramatically accelerates the calculation, leading to faster solutions. So an example of this was provided by Pierre Romanet and Arshabat, describing the evolution of ruptures on a network of faults with structural complexity, where these calculations can be done efficiently. Another approach to accelerate the calculation in the quasi-dynamic regime is to consider again the spectral method. So instead of representing the static term by integral, we conduct this operation in the Fourier domain that becomes a multiplication. And these transfer functions in the Fourier domain oftentimes have a closed form solution. So an example here is for a fault embedded in a compliant fault zone in a two-dimensional space, for which the relationship between slip and stress can be found in closed form that involves the rigidity of the compliant zone, the rigidity of the surrounding rocks, and the thickness of the compliant zone. So using the Fourier transform, the fast Fourier transform, we can attain these solutions quite efficiently. So an application of this spectral boundary integral method with the quasi-dynamic approximation is the exploration of stress interactions between neighboring faults that are parallel to each other. So they are meant to represent the network of faults in Southern California. And their stress interactions leads to clustering of events that is not observed when they operate in complete isolation. These calculations are done with open source software that is available at this link. The quasi-dynamic boundary integral method can be augmented to combine surface elements such as rectangles and triangles and lines representing faults, combined with volume elements, cuboid, tetrahedra, prisms, that represent the accumulation of plastic strain in the surrounding volume. So this is useful to represent the mechanical coupling between localized and distributed deformation, accounting for viscoelasticity, poroelasticity, and the presence of a free surface. So an application of this integral method, so now there's no boundary because it involves also volumes, is calculation of seismic supercycles at the Japan Trench that include the mechanical coupling between frictional sliding on the megathrust and viscoelastic flow in the oceanic lithosphere and the mantle wedge. So this is useful to represent the earthquake dynamics, but also the deformation that happens in the aftermath of earthquakes that can be documented with increasing resolution using geodesy. Okay, so now we start a rapid tour of methods that are based on the discretization of the volume surrounding the faults. The first of which is the finite difference method. So typically in the finite difference method, the governing equations are approximated with the finite difference operators. So the derivative at any point will be approximated by the difference between neighboring samples. So one way to do this is to consider a rectilinear mesh, a logical mesh that is mapped to a system of coordinates that maps to a curvilinear fault geometry and mesh geometry. So even though simple finite difference operators are engaged, this method is amenable to realistic structural settings with curved faults and complex structures. And so the governing equations translate into algebraic operators that can be solved with various known techniques. So an application of this was provided by Dal Zilio, considering a two-dimensional continuum with finite difference that combines fault slip, but also off-fault deformation with viscoelastoplastic rheology. So this method works for two-dimensional media, for in-plane strain and anti-plane strain, with the quasi-dynamic or the fully dynamic approach, and can incorporate multiple faults. Okay, so an example here is provided for the accumulation of slip in seismic cycles on a megathrust below a wedge, with two different examples for the quasi-dynamic and the fully dynamic solutions. Another example was also provided by Dal Zilio that incorporates the full coupling between fluid flow along the fault, but also in the surrounding poroelastic domain, with the rate and state-dependent friction on the fault plane. So this illustrates the versatility of the volume-based methods to incorporate complicated physics on and surrounding the fault plane. A last example of the finite difference method was provided by Allison, which involves the simulation of the mechanical coupling between the brittle section of the continental lithosphere with a viscoelastic lower crust. So the system here keeps track of the evolution of temperature due to shear heating, and that modulates the depth of the brittle ductile transition and also the thickness of the shear zone in the lower crust. So that allows us to better understand the structural setting of the lower crust below strike slip faults that is otherwise difficult to explore in the field. So other methods based on volume discretization are finite element methods. So the so-called continuous Galerkin finite element method is based on a weak formulation of the partial differential equation, where the solution is represented as a polynomial for each of the elements of the mesh. In the continuous Galerkin finite element method, the continuity of the solution is explicitly imposed. So the method is extremely versatile. It allows a large variability in material properties, and it's very flexible with respect to the geometry of the fault and the surrounding domains. However, it is among the most computationally intensive method. So there is a trade-off between versatility, the number of things you can do, the physics you can introduce, the structural complexity you can represent, with the numerical complexity of the method. So an augmentation of this finite element method that helps towards more rapid meshing of complex structures is the Discontinuous Galerkin finite element method. So FEMDG, discrete Galerkin. And so the difference here is that the solution is allowed to be discontinuous across element boundaries. So it affords even more variety of mesh types, and it naturally accommodates faults, which are discontinuities in displacement. So with this, the meshing of complex fault topology becomes trivial. And in this example, you can see how faults can branch into different segments and with bifurcations and even triplications at some locations. The disadvantage, of course, is that, well, it is even more computationally intensive. So more development is needed to accelerate these methods. So this is an example from publicly available code that implements the continuous Galerkin method with the spectral element method. And it's a two-dimensional, fully dynamic seismic cycle simulation on a strike-slip fault surrounded by a compliance zone of various geometries. The code is available at this link. This is an example of the discontinuous Galerkin method that is applied to a very interesting system involving numerous splay faults that splay off a basal megathrust that is applicable to a typical fold and thrust belt tectonic setting or the accretionary prism of subduction zones. And you can see how the slip across this system is segmented among the megathrust and the various splay folds of different sizes. So this is also a publicly available code called Tandem, which is available at this link. Last, we have hybrid methods that combine different numerical methods to optimize their different advantages. And here is an example from Abdel Megid and others who combine the versatility of the finite element method to the numerical efficiency of the spectral boundary integral method to compute the seismic cycles of earthquakes on faults embedded in a compliance zone. So the finite element method allows all sorts of complicated interactions within the fault zone that's completely captured numerically. But once the waves radiate outwards away from the fault and stop contributing to the stress change on the fault, they are dealt with the spectral boundary integral method that radiates them away from the fault. So it combines these two different approaches to calculate these models very efficiently. So we've introduced a number of numerical methods that are can be classified into discretizing only the surface of faults or the surface of faults and the surrounding volumes, so boundary-based or volume-based methods. You can see that there is a lot of different flavors of these methods based on the various approximations that are being made that enable further simplifications of the numerical methods. So currently, the most computationally efficient method is the spectral boundary integral method to calculate seismic cycle of a single fault plane. And the most versatile is volume-based methods using finite difference, finite element, or continuous or discontinuous Galerkin methods. But they are also the most computationally intensive. So choosing which method towards a solution is based on what simplification can be afforded and what numerical technique is available. So there's a number of publicly available codes that implement a variety of these techniques. So this is a list that is probably incomplete, but I encourage you to check out these codes and learn from how these methods have been implemented. And I encourage all of you to develop your own methods, making it publicly available so that the community can use them. So I'd like to say another few words about how to set up input files and how to choose boundary conditions, material properties, frictional properties, and other things, so that we can better understand how these models are put together. So one first consideration is how can we discretize the fault or the surrounding volume? What are the criteria for a sufficiently fine numerical mesh? Well, a well-sampled, a well-discretized numerical model captures the finest length scales of the problem. And they are typical length scales that emerge from seismic cycle simulations, namely the nucleation size of earthquakes and the size of the rupture front as earthquake ruptures propagate outward. The nucleation size can be estimated, and it actually depends on the material properties. So we have different estimates available. These ones come from the work of Noda and Hori in 2014 that depend on the frictional parameters A and B. So when A over B is greater than a half, this first estimate of the characteristic nucleation size can be used. And when A minus B lower than 0.5, another estimate can be used instead. Regardless, the numerical sampling must be finer than these length scales. The length of the rupture front, the representative size of the rupture front, is called the cohesion length, can also be estimated. And it follows a similar scaling with the weakening distance, the rigidity, and the normal stress. So considering all of these estimates, the practitioner must make sure that the mesh must be much finer than these length scales. So these length scales emerge in simple contexts of earthquake nucleation, rupture propagation. In the context of seismic cycles, that's going to be additional heterogeneities that are emergent or structural that make the length scale of this simulation even finer. So it is still a matter of testing to make sure that the model converges with finer and finer meshes. And currently, we don't have a universal recipe to predict the mesh size that would work without additional tests. Another issue is how to choose relevant mechanical properties, right? So friction is a complex phenomenon that depends at least on the mineralogy, the temperature, the structure, the structure of the fault zone, presence of fluids, and other things. So it is still a matter of intense research, but there's a lot of laboratory work that provides at least a baseline for how to choose these properties based on the tectonic context. So we refer here to work that's been done in the laboratory to constrain frictional properties of granite, olivine, pyroxene, hornblende, serpentinite, shale, and natural gouges that were collected from natural faults, and many other work that constrain these frictional properties as a function of mineralogy. Other studies, in fact, identify the frictional properties by modeling of the deformation. So that can also be used to constrain the frictional parameters. And then that's just for friction. So if there is additional mechanism, poroelasticity, or even on the fault, like thermal pressurization or flash weakening, that involves describing the frictional properties of even more parameters. So it is not something that is straightforward and completely figured out at the moment. The distribution of normal stress is also complex and controversial and very much discussed. So there are many ways that we can choose the distribution of normal stress for a fault. We can consider the difference between hydrostatic and lithostatic stresses, but that gives rise to tremendous stresses. And if normal friction laws under normal conditions are applied, this leads to very large stress drops that is unrealistic. Another approach is to consider fluid overpressurization. So how does that happen? If the fluid diffusivity is low enough at shallow depth, it basically pressurizes all the rocks below, leading to a stress on the pore fluid that approaches lithostatic. So as a result, the difference between lithostatic and pore fluid pressure can remain constant for many kilometers. And that's actually been observed in deep wells in Taiwan. Another approach is to basically simulate the migration of fluids from the mantle to the surface and what pressure they would have based on different boundary conditions. The loading of the system is also varies from method to method. The boundary integral method typically introduces either a long-term background slip rate for every element. So that can be varied spatially. So different segments of a fault can have different long-term slip rates. Or that can be implemented with a rate of traction, right? A rate of stress per element. And there's typically a mapping between a rate of stress or rate of slip. For volume-based methods, a typical loading is to apply a constant, well, a prescribed displacement at the boundaries. This is presumably the most realistic case and the most amenable to having multiple faults that accommodate this boundary condition in a dynamic fashion. So volume discretization methods offer the most flexibility with respect to loading, but it is still possible with the boundary integral method to have complex loading if we actually discretize the boundary condition with boundary elements. But a desirable goal where this field is going is to be able to connect the loading that is predicted by long-term geodynamic models with numerical simulations that simulate the short-term seismic cycle. The geodynamic model can predict where the faults are located and what their long-term strain rate is. And so this is information that we can hopefully one day incorporate in short-term models to produce more realistic simulations. These methods are sometimes emerging, sometimes mature, quite mature, and there's currently a large effort from the Southern California Earthquake Center to benchmark these different methods against each other in a community effort called the Sequence of Earthquake and Aseismic Slip, which is currently under its 7th such benchmark. And so I invite you to participate to these benchmarks. The link is available there. Contact the leaders of this working group and contribute with your code. But additional benchmarks are required to test a wider range of problems that are relevant to different tectonic contexts, subduction zones, continental transform, oceanic transform, so that we can test different physics and different boundary conditions. So to conclude, there is a number of numerical methods that are available to simulate seismic cycles, including methods based on the discretization of the faults themselves or discretization of the volume that surrounds them. So the degree of simplification of the problem dictates the most efficient method that is relevant for this problem. with the spectral boundary integral method being the fastest, the most computationally efficient, but limited to a single fault in an elastic full space, and volume-based methods being the most versatile, but also the most computationally intensive. To make proper numerical simulations of the seismic cycle, the discretization must resolve the finest length scales of the problem, which oftentimes ends up being the cohesion length at the rupture front. But other very fine length scales can emerge when additional physics are considered. For example, when shear heating is considered or off-fault diffusion. And because the seismic cycle engages such different timescales from milliseconds during rupture to centuries during the interseismic period, having the capacity for adaptive time stepping is a must. So the seismic cycle working group in the following years will guide developers as they make open source software available to the community while keeping full ownership of their own code. We will discuss all of these methods in much greater details in the seismic cycle modeling online symposium, and I look forward to seeing you there.